Wonderful. Second talk today will be with Niall Taggart, who will speak on Koszul duality and norm maps. Please.
Awesome, thank you. So I can start by saying everything I'm going to say is joined with Conor Malin. I want to give you a biased perspective on Koszul duality, norm maps, and functor calculus, and then tell you that my biased perspectives all agree. This doesn't make them correct. You can decide after if you think they're correct. Okay, so functor calculus is about, well, functors. So let's say I start with some functor from C to P, and the point of calculus is to assemble better and better approximations to F. You have something like a zeroth approximation, and a first approximation, and so on. Something like this, and you want to understand something about your functor f through this sequence of approximations. Okay. So, for homotopy theorists, we're given some sort of sequence like this. What do? We take iterative fibers everywhere. So we look at the difference between successive approximations. We say, okay, maybe we can't compute what these things are, but we can have to go computing what the layers are and try to assemble something about the original functor from that. Okay, so usually these all look the same. So I may or may not have significant loop space. So I may or may not have some infinite loop space. I have some speculative action of some group N. I have some sort of stabilization, which I want to think of as a function of S from C to spectra. And I have some fucking tensor product, but doesn't really matter. This inherits that action by this group Gn, and I take the homotopy orbits of that action. For example, if
sorry, is Gn Sn?
Gn is right now just some group. It depends on the examples of C and D as to what exactly Gn will be. So if C were if C were pointed spaces, and then S is actual stabilization, and Gn is the symmetric layers. If C was spectra, then S would be the identity, and again we would have the symmetric layers. And if you funkier things, it could look something like algebras over an opera. In this case, the suspension, the stabilization functor is topological analytic cosmology, and surprisingly, we get the symmetry again. So if you're in this setting, this is what people call duality calculus. But if you take something different, I can take what I'm going to write as vector 4, which by mean finite dimensional clear product spaces are symmetric embeddings. But it's basically vector spaces. In this case, the stabilization functor is a dimension of one point compactification. Right, so just take my one point, take my vector space at one point compactify to its instructions. And the group here is the orthogonal group. If you're doing this, you're doing what I would call flex. Okay, so the goal is to somehow understand these layers in these various examples, preferably all at once. So I guess I can tell you first of all that these spectra with these group actions are somewhat computable. Not like this abstract thing that I can't get my hands on. Somewhat computable. Okay, so basically for the entirety of my talk, I'm going to work in this bottom example. This is the ones I can remember off the top of my head. And in many ways, it's the hardest one to compute in. So there's somewhat computable there, there's somewhat computable there. So we could take, for example, the first derivative of the function O, which sends a vector space to the classifying space with its operator. This turns out to be the sphere. Okay, so reasonable. And we can take the second derivative of the same thing. This turns out to be a G suspension of the sphere. Anyone want to guess at the third derivative? Please.
Isn't it M2?
Nope.
No. It's been years. More spectrum.
It's loop 2 on the mod 3 more spectrum. So in particular, the sequence is the less enough. You cannot define the terms of the sequence from the first two terms. Weird things can happen. Okay, so what does somewhat mean? And let's look at, for example, the first derivative of B top. So here I send a vector space to the, I guess, we can classify space of homeomorphisms of that vector space. So it turns out that the first derivative of B top is a theory of a point. And so rationally, this is the part where you see that I'm in the center of these. It is the algebraic K theory of the integers. So, okay, the first one of this is pretty bad. You can ask me what the second one is, and the answer is no. Generally, no idea. It's no one rationally to work with transaction around Williams, but other than that, no clue. So they're computable, but only up to some horribleness that seems to happen in the examples you care about at 2.
Is the O2 and O3 action above?
Trivial.
Trivial.
Yeah.
Okay.
Maybe not on the O3, but I think on the first two is trivial.
Well, I mean, O1 is not so exciting.
Yeah. Well, you could argue it's the only group.
It's a bold statement.
It isn't being recorded. Too late. Okay, so we want to try and understand this homogeneous piece. So let's look at the fiber sequence. So I have the following fiber sequence. Let's, for the sake of being correct, assume that Gn is minor. Okay, so I have the following fiber sequence. The one thing I could do is, well, okay, I have some spectrum and I'm taking 104 bits. There's a pretty nice map out of this. So I could just map this by the norm map to the homotopy sequence. Okay, this is something I can do. Anyway, it's an approximation of this hard thing, but something maybe a little bit easier to compute. And the question I want to answer, which is where you're going to see that I'm in fact Dave Barnes' student, and I'm also going to draw a box on the board. And the rest of the talk will be filling in that box. This was not planned. So the question is, what goes here? And it's something you could call the fake tower. So one thing you'll notice as this talk proceeds is that tower is a very hard word to say with an Irish accent. So for me, this is tar. So if you hear tar, this is what I mean. If Dave couldn't speak Polish, I can't speak English. So we're doing our best. Okay, so the kind of moral is that the obstruction to being able to say that the tar, there we go, is the fake tar. This obstruction completely lies in, I guess, what you could call, all of the GN Tate data, right? If this map were an equivalence by induction, I could show that each of these things agreed. So really, understanding this thing that's supposed to be more computationally accessible, it actually gives a good approximation if you can understand what the Tate data is. Okay, so the question is, how do I build such a thing? So I should also add a small disclaimer, is that if G is compactly, then the norm map doesn't look like this anymore. I have to add in a dualizing factor. So the norm map takes this form where this dualizing factor is just non-equivariantly at least the 1 point compactification of the, again, the adjoint representation of G. So it's a non-equivariant sphere. The dimension of G is a manifold. So in particular, for G compactly, this is invertible. So I'm allowed to move it over to the other side and just take a spanning wet head dual, which is what I do quite often because I want to homogeneous things on one side. Okay, are there questions while I erase? I was also committed. In fact, encouraged.
You said the homotopy were more computable. In what sense is that?
In the sense that I needed a story for the talk I'm giving. That's why.
That's a nice bias.
I mean, none of these things are computable to me. Right?
Question.
Yes.
So in the context where it's like, I think spaces to spaces or maybe pointed, Nick Kuhn showed that when you have such equivalences, the tower splits. Is
Yes.
that true also in the other context that you were making?
If you have such equivalences, yes.
Okay.
Right, but this is why Tate vanishing TN locally. This is only true for finite groups.
Oh.
Right, so for example, for ON, it's not true anymore.
Thank you.
Okay, so the idea to build this fake tower I want to propose to you is the following. That we should approximate R calculus for some definition of R by manifold calculus. So the second thing is all about computing the space of module maps between modules over an operator. Alright, so I want to kind of replace the actual tower with something that looks kind of like a manifold calculus cell tower. It's all about module maps for modules over an operator. And the idea, I guess, with most things in calculus is back to arranging. And I'm going to kind of paraphrase what they say in their collection of papers. So the first thing to note is that, let's say f is a function now from pointed spaces to spectrum. What they notice is that the derivatives actually form a right module over the derivatives of the identity, where I take the identity on pointed spaces. Yeah, that would make sense. in fact, they're bimodule over the derivatives of the identity here, and the derivatives of the identity here, but here, the derivatives of the identity are 0. So just get a module over this thing.
Slightly type confused, like bimodule and symmetric sequences under composition.
Yes, exactly. You have to do a relative composition out here because they're trivial there. But in general, I have something from people. Yes.
Did you say R was for right? Or is that?
Yes, always for right. Um, not derived. Well, actually, everything is derived, so it's for both. If you say wish. And so what they do in this series of papers is they construct a fake car, and they show it's the closest approximation to the actual one. But built out of only the module structure. So they build it just using the fact that the derivatives of the functor are a right module, and they show that it's the closest thing that you could build to the actual tower just using that structure. Okay, now the problem you have is that if you want to do it in some of these other settings, so for example, when you deal with the orthogonal group and you want to do price calculus, is that you don't have operands anymore. So you have to somehow replace this whole story with an operand with something else. And so that's kind of what I'm going to go towards. Okay, and the way to do this is the following observation. So I can look at this category of right modules over this operand. And it's either a definition or a theorem of Michael Chang that this is the same thing as right modules over the spectral Lie algebra. This is the operand in spectra whose homology is exactly the Lie algebra in the Abelian groups. Our algebras over this operand are the algebras in the Abelian groups. Okay, think about algebra for a minute. We can start thinking about Koszul duality. And the Lie operand is Koszul dual to the commutative operand. This is the same thing as right modules over the Koszul dual of com. So this receives a map from right module over com. Okay, I'm called Koszul duality. Send right modules over com, I apply Koszul dual to a right module, I get a right module over the Koszul dual. And what Greg and Michael observed is that you can build either here or here with a car, and they agree. And somehow it doesn't matter if I work with right modules over com or right modules over derivatives of the identity, because the duality will tell me that the two things I build are the same. And this is not obvious, and it's basically the entire point of many of their papers, is to show this fact. Okay, so I can kind of take this, it doesn't matter which side of Koszul duality I am on, and replace all my operands with calculus, write down what Koszul duality should be, and show you that the same statement is true. Okay, and so how do you get from operands to categories? You observe the following. So if I look at right modules over an operand, this is the same thing as pre-sheaves on the envelope of that. I guess I want pre-sheaves and spectra, but no operand. Basically, if I have an operand, I can find a symmetrical category such that pre-sheaves on that recover right modules that we have. And so in particular, right modules over the commutative operand are the pre-sheaves on the category of finite sets. And kind of what we want is a Koszul duality for categories such that we recover Koszul duality for objects. So if I take this Koszul duality for categories applied to the envelope, I should get the classical Koszul dual of my operator.
So these for symmetric nodal categories or just arbitrary
I'm
categories?
going to tell you the class of categories for which you can do this for.
Okay, okay.
And it becomes nicer if you're symmetric monoidal, but I don't want to assume that. And in fact, really what I'm going to do is I'm going to give you a presentation of Koszul duality. It has a universal property. In a way that I'm happy to make precise outside of being live on the internet.
It's not the envelope of K of O, it's K of O.
Yeah, so I want some version of Koszul duality for categories where I put like maybe K cat. And if I do that to this category, I recover the classical Koszul duality for my class.
So K-cat gives you an opera.
K-cat will give me, if I put it in the envelope, an opera. Otherwise, it will give me one of these funky categories to which I can apply it.
So that means you might want to have an env on the right hand side of the equality on the outside. If the original K of O is just about syntax, but
That would also work.
maybe you
Just yes, probably I want that. Which I was in fact incorrect.
I think we're all a lot happier now.
And of course, the truth of this depends on how you define opera. We'll not go there. Okay, so let's talk a little bit about Koszul duality. Okay, so this is another place with the similarity between this talk and the last talk we taken. I want to look at what happens first of all in algebra. Okay, so I have some algebra over some field K, and let's assume it's augmented. So I have a map from a ground field. And how do I take the Koszul dual of this? Well, the Koszul dual of A is following pretty. I look at X in the category of A modules K to K. So this is the same thing as right A module maps from K to itself. Okay, so that's not so bad. I can just try and generalize each of these two things, right? I just need some kind of category with some nice augmentation, and then I just look at trivial modules when we're thinking of augmenting against as A modules with the module maps. And that's exactly what we're going to do. Okay. Yeah, so what's the point of this augmentation? Well, it's really the following data. It's mapped from A to ground field such that when I compare it with the ring map I have from the ground field to A, I get the Okay, so this were it's operands, or maybe if this were envelopes of operands, there's kind of a canonical choice of what to replace my ground field K. right? And it's the groupoid that you get from fragments. And so what I'm going to do is try and generalize that. Unfortunate, because not disappears. What I can start off with is trying to augment against some collection, I guess, of suspensions vector groups. And so if my groups were the symmetric groups, this would be trying to recover one of them. So I want some category C, and I want some maps like this, such that the composite is the identity. So I need this map to somehow be canonical. This ring map that will disappear was canonical, and the augmentation would just be that evidence. So to get a canonical map here, well, I can just ask that it be the identity of objects, and that it be the identity of the endomorphism. So I need C to have the object of C be the natural numbers, and what I'm going to ask for is that maps in C and N are point if N is less than N, the group in the right degree if N is, and then just whatever else they want to be if N is bigger.
So C spectrally enriched,
Yeah, I guess I want to see.
and when you write G star, that's also somehow thinking of this collection as a spectrally enriched thing.
Exactly. Because the last chicken is exactly right most of it. Exactly. So okay, this is like a spectrally enriched everything. And everybody's working on it doesn't matter what you mean by spectrally enriched. You take any of the things you can say spectrally enriched, and it works. So it works one categorically, but you have to be careful with model structures. It works in any of the models for spectrally enriched infinity categories that you could ask for. Okay, so examples of such things. And there's two I care about. So the example of opera, if I need to say my opera is reduced, is a, okay, I'm going to call these G star categories. This is a terrible name, but that's what we've got. In the paper, we call them augmented, and got an email saying we were evil. So, the refute is a sigma star category. I mean, I've been called evil a lot, but like this is the first. I don't know why I put the mic for that one. Okay, and the category that I want to call O-epi. So you should think of this as an orthogonal version of epimorphisms. So in particular, it's what I called vector, but with the top F is an O star. Okay, so the point is that like if I wanted to do opera, I don't have to do any of this because pre-sheaves on G star are basically or are exactly symmetric sequences. And they have a composition product, so I can make an opera with the relative to this composition product. But if I want to look at orthogonal sequences, which is what pre-sheaves on this thing would be, there's no good definition of composition product. So you have to kind of do something a little funky. And this is the funky thing we came up with. Okay, so the point is that as soon as I have an augmentation, I can start talking about equivalent homology. And that's what I will do. Are there questions while I do this?
I guess I have a question, which is what does the augmentation like actually look like for onto an opera? Like say for on with
That's a very good question. I do not have a good answer on the top of my head. I assume it's in the paper. Okay. And make it claims that it is in there.
So can you say again what example 2 means?
So it means that if I look at the collection of groups, which is just the group point on the suspension spectrum of the orthogonal groups, that I can define a map from this opposite category into that.
So what is that category? That's just...
I mean, okay, so I take finite dimensional inner product spaces with linear isometric embeddings, I take the opposite of that.
Okay.
Yeah, it's the suspension spectrum on the morphism spaces to make it a spectrally rich thing, but okay. So the point of the augmentation is that it gives us a derived in decomposables. So for example, if I have good right module over such as C to just be pre-sheaves on C, and then I have pre-sheaves on C and pre-sheaves on G star, and left hand extend along the augmentation or restricting it. So I could in fact call this left hand extension in decomposables, or maybe something like TAQ. And this restriction trivial. And this is given such a pre-sheaf on G star, this gives it the trivial C module structure. It's left between those. Okay, so why do I call this indecomposables? So if I take I take or a right module is an operand, then indecomposable in this sense is exactly the topological angular phenomenology of. It actually recovers the invariant that we know about. So I guess the equivalent, I want to say this is like the bar construction or what. Something like that. That's really my definition. Oh, would make more sense.
I think R
Yeah.
Yep. You know, so I'm live in front of a room. You can tell me anything, and I'm like, yeah, I agree. Anything to make it happy. Where was I going? I don't even have like a jet lag excuse or anything. This is okay, so the Koszul jewel of these are category C is, well, I could look inside right module in C. And I can just take the full spectral inverse subcategory generated by the trivial groups. I want to be careful, and it should be off in one place. So I'm going to put it there. Okay, so usually I have symmetric monoidal. And so this will reduce to just being the full spectral inverse subcategory generated by this on G1. So it does actually give you what you think it should. Okay. So this is really a present representation of what this thing is. It's not, I mean, it's supposed to be some kind of co-endomorphism operator type situation, and it turns out that it is. You just have to think much harder than I'm willing to do live to justify that thing. But if I were to look, for example, at this for the envelope operator, this is not defining a category, this is still a G-star category. And I can look at the morphisms from n to 1. And this gives me one and two. So I guess I'm trying to tell you that this is the classical Koszul. It's kind of like a dual bar construction. So I need to tell you why I can extend this to modulus. And if you think my analogies up to now were shaky at best, buckle up. Okay, so everyone here remembers very well for your analysis, right? Good. That's what I thought. So I want to do that.
So obviously the local category we're from.
Exactly. So the slogan I want you to take away is that an extension of Koszul duality to modules is really for any analysis, maybe for any transforms with characters, the set of these trivial modules on the sheet. So what does that mean? It's a good question. What do I do? I take a right module over C, and from this I want to produce a right module over the Koszul duality C. And I do this by sending this module to, so remember this is generated by the trivial things, so I just have to tell you where the trivial things go. And I send trivial and to right module maps in C from or to the trivial in G. Okay, so suppose to think of this as some kind of dual Fourier transform. So the question I can hear on everyone's lips, but they're just whispering it, is does it work? And I want to tell you that it does. And in a couple of ways. So maybe let me tell you the key features. So the big question when you're doing Koszul duality is on what things is this an equivalence? And so with respect to an equivalence, respects to an equivalence on levelized finite. This is just this R where or n as its spectrum is finite. Okay, it would be very nice if, for instance, if I took the Koszul duality C and then took, I'm also definitely missing an ops somewhere. There's going to be many missing ops. The exercise is to find it would also be great if you could read the paper and find them as well. So it turns out that if I take the Koszul joule of some G-star category, and then take the Koszul joule of that, I get my category back. Which really is what you want. And the final thing that gives you a glimpse of its universal property is that this thing is a lift in some sense that I can make precise. I take a TAQ of, or I take a spanner, I take a joule, and I smash it with the dualizing spectrum. I guess. I guess maybe this is this hat. So this is my justification for this Koszul duality being computable. Is that I've written that's invariance that people know how to compute. Okay, so I want to spend the rest of the time talking about how you can use this to build a fake talk. And particularly in bias buttons.
The lift, you mean that's somehow the norm of one is the other, or?
I mean that, so this is going to land in, I guess if I make n the variable, symmetric sequences, or G-star sequences. And this is a lift because this lands in modules over the Koszul joule C. And there's a forgettable functor from Koszul modules over the Koszul joule to G-star sequences because it's a G-star category. And the same diagram you build from this information commutes. And in fact, this Koszul joule is the universal thing to make such a diagram commute. Okay, so any other questions before I continue?
For the K of C being C, do you also need to add a finiteness for that? Some kind of spanning lighter dual.
Yes. It do need some kind of finiteness, but I think it's built into the definition of C having like morphisms back into suspension vector or something like this. Okay, so the rest of the talk is going to be with the following situation. I can say more when this is not spectral, but for the sake of it being understandable, let's take the spectra. So I want to construct the derivatives of the Koszul joule of something, right? Because that's what everyone Shane did, and it's good enough for them. It's certainly good enough for me. So let's define the Koszul joule derivative. And again, I'm going to call this partial upper. And this is again going to be some sort of Fourier transform. Which argues I want to look at the suspension spectrum of one point of magnification where I shifted by n. So I guess I should rewrite suspension spectrum of S or n tensor. Okay, so what does this look like? It's a good question. So partial upper star of F is when I look at natural transformations from F to S star. So maybe and where I'm dropping the suspension spectrum and I'm solving to do it. Yeah, it turns out that if you look hard enough at such a thing, this ends up being a module over this category co-epi. This basically comes from the spheres will be functorial in F. So, okay, so this is a module over epi. I'm saying it's the Koszul jewel, I guess. Probably that. Is a module over, to be more precise, rather than even degree 10. So I'm calling this Koszul jewel derivative. That'd be a very silly definition if it wasn't Koszul jewel to the derivative. So it turns out that it is. So what I can start with is just category functors. I can take the Koszul jewel derivative and run in right modules over epi. And then I can apply Koszul duality and right modules over Koszul jewel of epi. And this composite is equivalent to the derivative. Again, I've lost it off somewhere. Doesn't matter as long as I put it in one place, right? And so in particular, the derivatives naturally have the structure as a right module over the Koszul jewel of the. So we're exactly where our own chain were in this setting. We have some module over something. So maybe I'll say in words how the proof of this goes. You can restrict to representative functors just by an extension of colimit type argument. The Koszul jewel derivatives of representables are very easy to calculate. Koszul duality of that thing is very easy to calculate. And the derivatives of representables actually come from Miller's stable splitting of Stiefel manifolds. It's not how he phrased it at the time, but it's what he was doing. There's a paper of Gregg that makes that idea precise. Okay, so this is good enough to say what the fake tar is. So I have. So again, in the situation, it doesn't matter if I build the fake tar and right models over the Koszul jewel or just right models over the G star category. So I'm just going to do an easier one. And so this functor from functor category to right modules over Lassie.
So can I just check in vector are your morphisms or what? Linear isometry?
Yes, exactly. I'm technically identifying with a skeleton so that I have naturally numbered indexed things. Like in one case, I'm identifying with a skeleton on heteroepi, and in another case, I'm not. And so you kind of have to be a little careful. Okay, so I have this functor taking Koszul jewel derivatives. Now I've drawn it raised up a little, which indicates that it has a right adjunct. We call this. Okay, so it has a right adjunct. So what I can do is I can look at the unit of this adjunction. So it goes from F, let's say FB, to I'm going to get this the wrong way around. To this. Okay, I'm going to say that this is the infinite approximation F in the space. Now, if you sit down, what this is right modular maps. It's very heavy. And now I need to get my directions right because I should up. The Koszul dual derivatives of f with this. Okay, so the Koszul dual derivative actually land in up. And so that's why my things would swap. Okay. So now I have some space with module maps, and I can just run the kind of manifold calculus story and start truncating the space with module maps. So I can say P and fig B is just right module maps. No mapping. I'm just going to truncate on the code domain. Do something like this. So in exactly the same way as manifold calculus works, it's very easy to show that the limit of these things recovers exactly this thing. It's just how get a module can just add on the term this thing. And there are, I guess I want. So they're basically as compatible as you want them to, because the communication of modules is compatible. So what happens is I have a map from the nth term in the state prior to the n minus first. So with this being the unit of some junction, this receives a map from f, and that actually factors over the actual tar. Like so. So this is saying, in particular, that this functor is n polynomial, but just not the n polynomial approximation. Okay, I have a square. What am I going to do? I'm going to take either vertical or horizontal fibers. Here I want to take vertical, because that's the story I'm trying to tell. So I'm going to take the vertical fiber in both places. And I get an induced map. Now, this we computed. So the question comes computing this side. I've done that for you. If I can remember the formula. I guess I can cheat and take it out with the formula GP and I think what it is back. So I get the sinusoid the dualizing spectrum tensor with the M1 improvements. This comes from the fact that the Koszul dualism module was sublit the TAQ where this dualizing spectrum is also here. So you compute hard enough and this is what you get. And I have a map. Is it the norm map? And that's really the hard part, which is the perfect time to just be running out of time. It's almost like I got it. So the kind of takeaway is, I guess I should also cut myself. That this map is the norm. Okay, the proof of this is there's a universal way to characterize when a map from orbits to fixed points is a norm map, and that's by looking at what it does on the suspension spectrometry group. It's the result of Quinn and Klein. So we do that. And we show that there's an equivalence there, and if you have some map that's an equivalence on that, it is the norm map. So it's really not ours, it's really finding food in different guises. Telling us this is the norm. Okay, so I've given you what I wanted to give you. I've given you some sort of fake version of bias calculus that's approximation to actual bias calculus depends entirely on the norm. So if G was a finite group and not O, so I can do the same story in all these other cases that I had at the start. It all works. And so if G is a finite group, this would say, for example, rationally, the tar and the fake tar are the same thing. Right? Or Tn locally, the tar and the fake tar are the same thing. It vanishing for compact Lie groups seems harder / not true. So it doesn't tell you this. It tells you, for instance, if you plug in a representable, then the fake tar are representable and the actual tar are agree. But kind of not much more than that. And I kind of the point of this whole exercise is this composite, maybe after I take Koszul joule, is a comonad. And this kind of square that you build here, building the tar to the fake tar, that you classify polynomial functors as coelegant over that comonad. So you can basically run the entire room chain program, not in situations where it didn't apply. So there's even this work of Lanz and Bloom on how the derivatives are a lax monomial functor from the infinity true category of differentiable infinity categories to PRL or something. So they can run the room chain program in this like infinity category generality, but bias calculus doesn't fit into that framework. So in particular, what we're doing here is something different to what other people have done. And we're nonsense. Okay, and I'll stop there.
Questions? The fake tower discussion here, is that analogous to what Aron and Ching do? I mean, you get a comparison. So how is theirs?
It's exactly the same thing.
But for O instead of KO or
Exactly. So
okay.
if I put here finite sets, so the envelope of like column, it would be exactly how they construct it. I think they actually do it on the Koszul dual side, but it doesn't.
So if I took some other sequence of compact Lie groups, do I stand like no one can make a new version of orthogonal calculus. Making new versions of orthogonal type calculus is really difficult.
I agree.
But
the fake.
for the fake version, what do I need? Like a sequence of groups?
Yeah, exactly.
And then I just
I mean, the point is that if I take this sequence of groups to be the orthogonal groups, and do like equivalent S inverse S construction on this,
Yep.
I get the category of vector spaces out again. Right? So that's how you construct the calculus from just this sequence of groups in some way. So it's not clear how to make the entire orthogonal program run, but certainly that's enough to make the fake set of
and it's going to work for UN obviously,
Yeah.
but if I took some other class sequence,
it'll still work.
It's maybe want your groups to form like a model group or something.
So it didn't use any symmetrical modality here, right? It will work and will be nicer if your groups form a symmetrical groupoid, but nowhere in the story did we use symmetrical modality.
no connectivity on the groups as n increases.
Do you need the suspension spectrum to be dualizable in spectra for the groups?
Yeah, but that's true if I'm compactly,
Yeah.
right? So I challenge you to choose a group that's not compactly.
Yeah.
Compactly with a discrete topology.
Let's see.
Okay, you win.
And it's finite if it's a compact Lie group with a discrete equality. So the B top example, what is del upper 1 for what is some other dual of A of a point here?
I have no idea. I think it should be relatively computable, but I don't know how to do it.
Do you have a formula relating the partial upper star to the thing that's
Yeah, so
top of the board?
it's partial upper star. I take partial upper star and then apply Koszul duality to it. So that's like, first of all, I look at natural transformations into this thing, and I look at natural transformations from this thing viewed as a module into the trivial thing. And then I have to compute that. So by adjunction, it boils down to computing some kind of TAQ of something. With that particular example, I don't know what the answer is. I know very few of what the answer is. It also depends, like, you have to really be able to compute what K of F actually is with the category. And I have no idea how to do that. In the paper, there's a conjecture that we got from Greg. I don't understand the conjecture. So I think it's difficult.
Can you repeat what you said about the Miller splitting?
Yeah, so Miller splitting is computing the derivatives in our orthogonal calculus of the representable functions.
Okay.
This is not easy to see, but there's a paper of Greg's where he shows that if you have a functor that satisfies some properties, it splits with the product of its homogeneous layers.
Okay.
And one of the properties of this functor has to have some kind of filtration. So if you take the representables and give it the filtration that Miller gives, it satisfies all of these properties. And so Miller splitting is this functor splits as a product of its homogeneous layers, or a wedge of its homogeneous layers, doesn't matter. And that, from that, you can extract what the derivatives are.
What can you do with a fake tower? What is it useful for?
That's a very good question. So we used it to do this classification of coalgebras. We'd argue this is not useful because you can't really figure out what the code is. But the idea is that many things can improve the fake tower. Right? So for the fake tower, if you allow symmetric linearity, you can improve like product rules almost instantly. Right? And you want to try and pull that back somehow along the fact that it classifies it as a coalgebra to get product rules for the actual functors. There'll be some sort of understanding of what Koszul duality does in symmetric model.
So it's less of a computational tool.
Well, certainly for me, it's less competition. Other people are welcome to use it in the competition. I encourage them to do so.
So you use this result of Brenda Johnson that the Koszul derivatives of the identity is the Lie operand inside there. So that is the Koszul dual statement then easier to prove? Would that be that del upper star
Yes.
of the identity is com?
Yes, this is much easier to prove.
Yeah.
It's like 2 lines to prove.
I want to use it very much not as a computational tool, but as a theoretical thing. And I want to do Koszul duality for spectrally enriched categories. What do you really need for the category? Because you were saying you don't need it to be symmetric monoidal, and you are assuming that the natural numbers are, like the set of objects is the natural numbers. But could
I don't need this. I need, in fact, you're probably the person to ask what I need in order to do this, which makes this question complicated.
Well, I am asking, so I am the person.
Ask yourself. Huh? I need that the underlying groupoid is free, and then I need some freeness condition. Something equifiber is what I was supposed to say.
Shall we continue over wine on the other group after thanking the speaker again?
Yes.